Hi everyone, welcome to our fourth lecture. This lecture is on 1D kinematics applied to simple harmonic motion. It's again a joint lecture between the Calc and non-Calc students. The Calc students will see an extra section on calculus which will be edited out for the non-Calc students. The reason I do it this way is to produce uniformity between both classes with the extra calculus that's required for the Calc students. Okay, so let me just quickly remind you what we've done with kinematics so far. 2 lectures ago, we did 1D kinematics. We did the general theory, where I defined position, velocity, and acceleration. But because it was a general theory, you really can't do much with it. Certainly the non-calc students really can't do much except to calculate maybe some like average velocities and average accelerations. Even the calc students are limited because it requires some difficult mathematics, differentiation, and for some simple illustrations you can do that, but it can get very complicated. And so even for the calc students, that's very limited. And so the last lecture, I said let's take that general theory and apply it to a specific situation, and that was the situation of constant acceleration. And the best example that we have of constant acceleration is falling. So when you drop something, when you first let go, it moves slowly at first, and then it speeds up, speeds up, speeds up, and it speeds up at a constant rate, a constant acceleration of 9.8 meters per second squared downwards. Okay, that's a very simple example of, and a very common example of constant acceleration. But there are other situations too, like another situation might be like a car driving and hitting the brakes. It would slow down, and that slowing down is a negative acceleration with respect to the direction of the velocity, and or speeding up. A car, say, at a stop and steps on the gas and then speeds up. Okay, so today we're going to do something similar to that. That is, we're going to take our theory of 1D kinematics and we're going to apply it to a special situation. And this special situation is called simple harmonic motion. Often you'll hear me refer to just oscillation or even vibration, okay? And so what is this situation? Well, this situation is just when something sits there and it oscillates back and forth like that, okay? So it just forever goes back and forth, back and forth, back and forth like that. And this is very common, okay? An example of this, and these are actually, this is actually an example that you'll see in the lab, is a pendulum. And so what's a pendulum? You just take a mass and you tie it to the end of a string, and you pull the pendulum, and it just bobs back and forth like that forever. Well, not forever. There's friction, which we won't consider, but if there were no friction, it would continue forever. Another example that you'll also do in the lab is a spring. Okay, so if you have a spring and you stretch the spring and you let go, the spring will bounce back and forth like that. You have to put a mass on, and the mass will tie like one end of the spring, say, to a wall, and the other end to a mass on a linear air track. So again, there's no friction. You pull the spring back and the mass will bob back and forth, back and forth, back and forth like that. Maybe a real world example is like the shock absorbers on your car. When you hit a bump, your shock absorbers will squeeze down and then they'll bounce back and forth. There's quite a bit of friction to try to damp out the motion. We won't consider that part of it. But the bouncing back and forth part of it, that is simple harmonic motion. But it's everywhere. Another example, one from biology, is the little cilia in your ear. These are these tiny little fiber hairs in your ear that will vibrate back and forth when they hear sound. Okay, and that's how we perceive sound in the ear. And you can refer to your biology course for more detail about that. But they're vibrating back and forth. Okay, if you have a glass and you just hit the glass, like a drinking glass, and you see that it vibrates, you hear it ringing, that's because it's vibrating back and forth. So there are just so many examples. And as usual in physics, we're going to just look at this in the abstract, okay? And so what you're seeing here is a diagram where I'm trying to illustrate simple harmonic motion, okay? And it's 1D motion too. And this loop I have here, I really can't draw the motion very well as a single line. It would just, you wouldn't see it. So I kind of expanded it a little bit, but remember, it really is 1D. It's really along the line here. And so you can imagine that the motion starts at this one end here. This is like, say, a spring, and I pull it out, okay, and then I let go. What does it do? It pulls back, and then it bobs back and forth like that, okay? And there is a center to this motion, x equals 0, okay? And x equals 0 is called the equilibrium. That's the middle of the motion, all right? Or if the spring were not stretched at all, that's where the mass would sit, okay? Right there. And x is equal to plus a. That's the maximum displacement that you would get to one side of the motion, on the right side of the motion. But you'll get the same on the left side of the motion. X is equal to minus a, okay? And again, it would just bob back and forth like that. And it would always be bounded between x is equal to plus a and x is equal to minus a, centered on the equilibrium, which is x equals 0. Okay, so there's a description of the motion, and let's start to make it more mathematical. You say, well, how would I describe such a motion mathematically? Remember, now we're starting to do the kinematics. We're starting to write down some formula that describes that motion. And equation number 1 there can actually be derived from more fundamental principles. We'll see a little bit of that later. But right now, let me just write down equation number 1, which is the position as a function of time. Okay, so there you go. The position as a function of time. And you remember from the previous lectures, all of our information about kinematics is packed into that formula, and we can tease out that information as we ask questions, like what's the velocity, what's the acceleration, and so on. And there it is. Okay, so there's equation number 1, and let's take a look at what goes into it. We actually won't use equation number 1 except in the theory. We'll use it to solve problems. Okay, so don't be too intimidated by it. But it's a cosine. Okay, and you know what cosines look like. They basically bob up and down. I've got a graph of it in a minute. We could have used the sine too. Sines and cosines have the same shape. They're just kind of shifted in time. Okay, but we'll choose to use the cosine for this course. Okay, and there's this capital A, and we already saw capital A. Capital A is called the amplitude, and it is the maximum displacement from x equals 0. Okay, so if I scroll back up to that diagram just for a second, you see here x is equal to 0, all right, which is the middle of the motion. And you'll notice that the maximum that the oscillator will move to the left or to the right is plus a, x is equal to plus a, or x is equal to minus a on the other side there like that. Okay, and that's the amplitude, all right. And t here, little t, well, you know what that is. That's the time. Okay, so basically you say, well, where is this thing at t equals 5 seconds? Well, a would be some number, okay, depending on the particular situation. A might be something like 3 centimeters or 7.5 centimeters or something like that. So a is a fixed number. And then you would plug in, well, t is equal to 5 seconds, and you would crunch it through, and you would get the position at that particular time. All right. You'll notice there's one more thing I got to tell you about, and it's this symbol right here. It looks like a W, but it's actually the Greek letter omega. It's actually curled in at the top a little bit, okay? All right, so you'll hear me call it omega, not W. It does look like a W, and I've tried to write it carefully so you can see it kind of curls in at the top, unlike a W. So it's called omega. And that's the hardest one to understand. It's called the angular frequency. All right. So there are two words here, angular and frequency. What do each mean? All right. They're both important. So first, frequency. You're going to hear the word frequency a lot in physics. Frequency, it's just like the colloquial meaning of the word frequency. It's like how often does something happen? Okay. Like, I don't know, with what frequency do you drink water or something like that? Or it might be a question that you ask in biology. Something like that. Okay, so how often does something happen? All right, the answer would be so many times, so many cycles per second. So, for instance, if we go up here and we look at this thing bobbing back and forth, if it starts here and it comes back there in 1 second, then it bobs once per second. But if it does 2 complete cycles in 1 second, then that's 2 cycles per second, or 3 cycles per second, or 4 cycles per second. So, like 4 cycles per second means that it would start here and would bob back and forth 1, 2, 3, 4 times every second. Okay, and it doesn't have to be an integer number. It could be like 4.5 times a second. And what does that half mean? It means it only completes a half a cycle extra. So it could be like 1, 2, 3, 4, and then another half a cycle before the second is over. Okay, so you'll see this in the lab. All right, that's what we mean by frequency. But then there's this word angular there. Okay, and the word angular actually means what I just said, but there's an extra factor of 2 pi. Okay, so I'm going to write this down as a formula in a minute, but the word angular frequency means it's not only the times that it bobs back and forth per second, okay, number of cycles per second, but also multiplied by 2 pi. And you would say, now, why did we do that? I mean, you know, this idea of a frequency was very nice, and then you go ahead and you put in this angular part to it. Why did you put in an angular part? And the reason is that if you go back to the cosine here, do you remember that in radians, so we're talking radians now, not degrees, in radians, the cosine makes one complete cycle in how much? 2 pi radians. That's why we introduced this extra 2 pi, okay? Now that might seem annoying, but in practice, you actually want to work with the angular frequency more than you want to work with the linear frequency, and the reason is that it comes up in the formulas a lot. In other words, omega comes up in the formulas much more than just the linear frequency. So now you heard me say a new word, linear frequency, and let me define 2 more quantities to make it very clear. So now you understand the angular frequency. It's 2 pi times the number of cycles per second. The linear frequency, okay, is exactly what I started. It's just how many times this thing makes a cycle per second, okay? So usually, you know, like in a lot of the course, we won't be worried about the angular frequency. We'll just be worried about the linear frequency. In cases like that, we tend not to say the word linear, which is why I put it in brackets. We'll just say, what's the frequency? What's the frequency? When in reality, what we mean is, what is the linear frequency? In these special cases, when you're working with the formulas, like that you'll see when you're working with omega, we'll be working with the angular frequency. So not to confuse angular and linear frequency, we'll call one the angular frequency, that's the one with the extra 2 pi in it, and the other one the linear frequency, okay? And then there's another quantity you should know about, and it's known as the period of the motion. Now these two are usually confused, so let's be very careful here, okay? So linear frequency is how many cycles it makes per second. The period is the time it takes to make one complete cycle, okay? And so let's go back to the diagram up here. And let me see if I can describe that, and then I'll show you the formula that relates the period and the linear frequency. Suppose that this oscillator, starting from this point here, in 1 second makes 2 cycles. So it'll go once, twice, and that's it. There's 2 seconds. So we start with our stopwatch, and the stopwatch is at 0, and we go click, and it goes 1 cycle, 2 cycle, and then when it gets back to here, we see on our stopwatch it says 1 second, okay? So it made 2 cycles per second. That's a linear frequency of 2 cycles per second, okay? What's the period, though? How long does it take to make 1 cycle? Well, if it makes 2 cycles per second, 1, 2, and 1 second, then to make only 1 cycle, it only took half of that time, so it's half a second. So the period would be half a second, the time it takes for 1 cycle, whereas the frequency is 2 cycles per second. Okay, let me see if I can clear that up for you. So let's start with the concept of the period. How long does it take to make 1 cycle? Half a second. That's the period, capital T. Half a second. So it starts here and it goes and it comes back to the same point. Half a second. Let's continue. And so another half second. A half a second plus another half a second is a full second. And how many cycles did it make in a second? Twice. Okay? Well, what if it did 3 cycles per second? So it would go 1, 2, 3, and that's it. That is 1 second. Well, then each cycle must be a third of that. Because if there's 3 of them in 1 second, then each cycle is only a third of the full amount. Okay? So then the period would be a third of a second, whereas the frequency is 3 cycles per second. Well, what if it were 4? Well, then it would go 1, 2, 3, 4 for 1 second. And that means that each cycle is a quarter of that, 1/4 of that. And so the period would be a quarter of a second. And I think you're starting to see a pattern now. If the period is 1/4, the frequency is 4. If the period is, capital T, is 1/3, the frequency is 3, and so on. So the relationship, what you can see there from that pattern, the relationship between the period and the frequency is they're reciprocals of one another. And this is the formula right here, okay? So the frequency, meaning linear frequency. So remember, if I don't say the word linear in front, we assume that we're just talking linear frequency. So the frequency and the period are reciprocals of one another. F is equal to 1/T, okay? And then finally, to bring in the angular frequency, we have this other equation here, which we can call equation number 2. The angular frequency denoted by the symbol omega, okay? So omega is equal to 2 pi times f, where f is the linear frequency. And if we replace the linear frequency with the period, we can also write that as 2 pi over capital T. This entire equation here encapsulates everything that I just set up above. Okay, so just to be very clear, omega, that's your angular frequency. That's what was in that formula. That's what was in the cosine. F is the linear frequency. That's what you would actually measure in the lab. Okay, in the lab you would say, you know what, I'm going to just count how many cycles this thing does in 1 second, and that would be your F, the linear frequency. If you multiply that linear frequency by 2 pi, you get the omega. And another way you could do it in the lab, rather than measuring the frequency, you could measure the period. How long does it take to make 1 cycle? And that would be capital T. And 2 pi divided by capital T, that's your omega. Okay. And again, that omega, why did we even introduce it? Why did we introduce that 2 pi at all? And it goes back to this formula right here. That's the omega that's in there. So let's come back to this, make sure we understand all of the pieces in there, just to recap what we said. So the position as a function of time is given by the amplitude. That's the maximum displacement from equilibrium, x equals 0, okay? And it's measured in meters, obviously, MKS, okay? Times the cosine of omega, which is that angular frequency, multiplied by the time, okay? And omega is the linear frequency with an extra 2 pi. Why the extra 2 pi? Because the cosine oscillates with a periodicity of 2 pi radians. All right? All right, there's the general theory. And the next section is for the calculus students only, okay? So now that we have the position as a function of time, all right? We have the position as a function of time. We ought to be able to derive a formula for the velocity as a function of time and the acceleration as a function of time. And you say, well, how do you do that? Go back 2 lectures, and you'll be reminded there that to get the velocity, it's the first derivative of the position as a function of time. Okay, so let's do that. We take the position as a function of time, differentiate it with respect to time. So there it is, d by dt, means we're going to differentiate. And for x of t, we're going to put in a cosine omega t. Okay, now a couple of things here. First, the a just comes out in front because the constant just comes out in front of the differentiation. And then we're going to differentiate the cosine with respect to t. But watch it. We're going to differentiate the cosine with respect to t, but to do that, we first have to differentiate the cosine with respect to omega t, and then differentiate the omega t with respect to t. This is known as the chain rule, okay? And so if we do that, what happens is so the a comes out in front, so you see that a there? There's the a there as part of an answer, okay? And then we differentiate the cosine with respect to its entire argument, which is omega t. And here I just called it z for whatever reason. Suppose that omega t would just say, call that z. So differentiate the cosine with respect to z, which is the entire argument. The derivative of the cosine is minus sine, okay, z. And so you'll see that you'll get a minus. There's that minus there. And then the cosine becomes a sine. And then you say, well, where did that omega come from? Because there's this extra omega out in front here. And after we differentiate the cosine with respect to omega t, we have to differentiate the omega t with respect to t. And omega t divided by differentiated with respect to t is just omega. And so we get an extra omega out in front, okay? And so just to summarize that, differentiating this entire thing, we get the a out in front, we get the derivative of the cosine, which is minus the sine there. There's the minus the sine. And then we have to differentiate the entire argument with respect to t, and we get an extra omega in front. Okay, so there we can call that equation number 3. And what is that? There's the velocity as a function of time. Okay, now continuing, we can now differentiate one more time and get the acceleration as a function of time. Okay, and so over here, we're going to start with the definition of the acceleration. It's the time derivative of the velocity function, okay? And so here we go. We're going to differentiate minus omega a times sine omega t. Same thing as before. We're going to bring that minus omega a out in front. Okay, so here's the answer. We're going to have a minus omega a out in front. And you go, but there's an omega squared there. I know, hold on. So there's 1 omega and a minus omega a. That's from before. When we differentiate the sine, we get just a cosine, so that sine just becomes a cosine, okay? But then when we differentiate the omega t with respect to t, we get an extra omega. So we had an omega there from before in the coefficient in front, and we get an extra omega when we differentiate the sine, and that's why we have 2 omegas there. And so the acceleration as a function of time is minus omega squared a times cosine omega t, okay? And we can call that equation 4a because you can actually simplify this equation, okay? And you can see here that there's a cosine omega t, and you go, isn't that just x? If, in other words, just ignore the minus omega squared here, just go a cosine omega t. Take a look at equation number 1 above in our notes, and you'll see that's just x. And so, and in fact, I just wrote it here, x is equal to a cosine omega t. And so I can take this whole piece here and just replace it with a is equal to minus omega squared times x, okay? And we can call that equation 4b. 4a and 4b, they're really the same equation, okay? Given that x is equal to a cosine omega t, they're the same equation. But, you know, in this particular form, it's very interesting because it shows that the acceleration is proportional to x, that is how far it's been displaced, how far the object is displaced from equilibrium. But it's in the opposite direction because there's a negative sign in front, and then there's also an omega squared in front as well, okay? And there it is. Now, I introduced the theory here you know, and showed the calculus students, you know, how that worked out. We actually are not going to use this for the problems that we're going to do immediately after following this, but in a few lectures, this will come up again, okay? So this, what I just showed you here, is not going to go away. It'll come up again in this semester. It'll come up again even next semester, okay? So and when we do waves, so don't just discard this just because you take a look at the problems that we're going to do in a minute. And you go, well, we never made use of this. We never made use of the sines and cosines. I know, but the theory just keeps coming up over and over and over again. And the reason it keeps coming up over and over and over again is, as I alluded to at the beginning of the lecture, there's so many things that vibrate, okay? And it'll especially come up again when we do waves. I mean, waves are all about vibrating things, okay? They're like actually infinitely many oscillators all connected to one another. All right, so yeah, I introduce it here because this is the place to introduce it. We won't need it immediately, but we will make use of it later, okay? So there we go. That's the end of the calculus portion of this. And so let's continue with the rest of the lecture. All right. Probably the best way to see what the position, velocity, and acceleration look like for an oscillator is to graph them, okay? And so what I have here is actually a graphical representation of the position as a function of time together with the velocity as a function of time and also the acceleration as a function of time. These graphs admittedly are a little bit hard to draw, but you know, I'll explain them as we go along. Okay, I kind of free-handed them, but there are probably better pictures online if you see them. But let's go through these, and I think they'll be pretty clear. The first graph I have here is the position as a function of time, like that. Okay, this position as a function of time. Now, the position as a function of time, the way we're doing it in this course is we use the cosine. Again, I mentioned that you could use the sine, but we're just going to stick with the cosine. And if you do a cosine omega t, and you set t equals 0 in there, okay, so you set t equals 0, what you're going to get is cosine of 0, and in my next slide, I'm going to go through some special cosine and sine evaluated at some special angles. But cosine of 0 is one of these special angles at which you should memorize the value of the cosine. Cosine of 0 is 1. Okay, you could try it on your calculator. Cosine of 0 is 1. Cosine of 0 radians or cosine of 0 degrees. But for this lecture, we're working in radians. So if you do that, you're going to get that cosine of 0 is 1 multiplied by a. You get that the position at t equals 0 is a. Okay. And now let's go all the way to the end here. If the oscillator has made one complete cycle, like that, how long does it take to make one complete cycle? Well, capital T. Okay, so by the time if you start at a, x is equal to a, and you end up at x equals a, the time it took to make that one complete cycle is capital T. And so this dashed line along here, this represents a time of capital T. Okay. Well, let's divide up the entire cycle into quarters. So if you start at x is equal to a quarter of the period later, so this is a 1/4 t later, you're at x equals 0. okay? At half of the period later, you're at x is equal to negative a. And at 3/4 of the period, you're back at x equals 0. And then at little t equal to capital T, that is when you've done a complete period, a complete cycle, you're back to a again. Okay, so that's what this graph is trying to show. And you can see here that I took the entire period, that's up to here, and I divided it into quarters. Okay, so again, I free-handed this, but I think, you know, even though it's not perfect, I think you understand, you know, how this graph is put together. Let's look at this, what I just described, but let's look at it back in the original picture that I had. So let's scroll all the way back up here, like this. And let's take a look at this. Suppose I'm right here, that's t equals 0. Okay, little t is equal to 0. At 1/4 of the period, I'm right here at equilibrium. At half of the period, I'm at x is equal to minus a. At 3/4 of the period, I'm at x equals 0 again. And at the full period, capital T, I'm back here at x is equal to plus a. Okay, so there you go. There's one complete cycle. All right, and so one complete cycle started, once again, started x is equal to a, x is equal to 0, x is equal to negative a, x is equal to 0, and x is equal to positive a. Go back to our graph here, which is describing that exact same motion. And here we are. X is equal to a, x is equal to 0, x is equal to negative a, x is equal to 0, and you're back at x is equal to plus a. Okay, there you go. There's a graphical depiction of the position as a function of time. How do we get the velocity from this as a function of time? And the answer is it's the slope. It's the slope of the tangent line at every point, okay? So it's the slope of the function at every point. So if we take a look here, you say, what's the slope of the function here? Well, we're at the top of one of these peaks here, okay? And you can actually see it even a little bit better here, like that, okay? And you say, what's the slope right there? What's the slope right there? It's 0, because if you formed a tangent line right there, that's at the very top there. That's like a flat line. A horizontal line would be the tangent line at the very top. And so the initial velocity right there, the slope right there, is 0. Okay? If you scroll down and take a look at the graph that I have below it, there you go. You see the velocity. This is now a velocity versus time graph, like that. So velocity is on the vertical axis. And as I just argued, the slope at t equals 0 is 0, and so the velocity initially is 0. There it is. You can see there, it starts off with a velocity of 0. All right. Now, let's scroll back up, like that. And you say, okay, well, as I start to come during the first quarter of the period here, as I start to move from x is equal to a to x is equal to 0, what's the slope? Well, the slope isn't constant. You know, it starts at 0, but you can see that the slope is always kind of negative, okay, until finally, at t is equal to 1/4 of the period, the slope becomes its maximum negative value. Okay, so it starts at 0 and it goes to, at 1/4 capital T, 1/4 of the period, it goes to its maximum negative value. Right? And so over here, you could see that the velocity starts at 0, and then at 1/4 of the period, it is at its maximum negative value. Okay, now it stays negative, the velocity stays negative because the slope stays negative along here. But by the time you get to half t, what's the slope at a half t? It's 0 again, isn't it? Because you get, if you put the tangent line there, it'll be a flat line, and a flat line, 0 slope, 0 velocity. Okay, so at a half t, guess what? You're back to 0 velocity. So you start at 0 velocity, your velocity goes negative. At 1/4 of the period, you're at maximum negative velocity, and then at half the period, you're at 0 again. Okay, now take a look at what the velocity looks like after that. You're at 0 velocity there. From a half to 3/4 of the period, your velocity is positive. Until you get to 3/4, and then you're maximum positive. And then from 3/4 of the period until you actually hit the full period, the full cycle, okay, your velocity is positive, but it goes back down to 0. Okay, so it starts at 0, goes to maximum positive velocity, and then goes back to 0 again. Okay, and over here, you can see that there it is. You're at 0 velocity, you go to maximum positive velocity at 3/4 of the period, and then you're back to 0 velocity again. Okay, and let's now see that in the diagram that I have up above. Okay, so let me scroll all the way back to my original diagram here. So let's start right here. And remember that the position at t equals 0 is a, plus a, okay? And then a quarter of the period later, we're at 0. Half of the period later, we're at negative a. 3/4 of the period later, we're at 0 again. And then at a full period, we're back to that again. What is the velocity at that end point right there? What is the velocity at x equals a? Well, let's think about it. The oscillator, before you're at x is equal to a, is moving to the right. After you're at x equals a, after you've swung around the amplitude maximum displacement, you're going in the negative direction. So 1 minute you're going in the positive direction, the next minute you're going in the negative direction, and guess what? In between negative and positive, you must have hit 0. So the velocity right at that endpoint there is 0. Same thing happens here. And I apologize, I just noticed that this arrow is in the wrong direction. Okay, so this arrow should be showing that you're swinging around like that. So let me just follow the arrow, follow my cursor here and swing around like that. Okay, so here you are at x is equal to negative a. And at x is equal to negative a, 1 minute you're going in the negative direction, you're moving along this way. Okay, the next minute you're moving in the positive direction and switching from negative to positive. In the middle, you must have passed through 0. And that happened exactly at x is equal to negative a. So at the two endpoints, x is equal to plus a and x is equal to minus a, your velocity is 0. Okay? Where's the velocity the biggest? When you're passing right through the middle. Okay? So when you're passing through the middle, going from plus a to negative a, your velocity is maximum negative value. And when you're going from negative a to positive a, your velocity passing through the middle is maximum plus direction. Okay, that's exactly what we saw in the graphs. All right, so let's swing back to those graphs there, like this. Let's go back to the graphs. And it's kind of hard to put them, I'm going to shrink this down just for a second. Okay, so you can see them all together. And let's take a look there. So this is when you're at maximum displacement at x is equal to positive a, your velocity is 0. When you're at x is equal to negative a, your velocity is 0. And when you're back at x is equal to positive a, your velocity is 0. When is your velocity the biggest? When you pass through x is equal to 0, the equilibrium. Okay? When you pass one way, it's maximum negative. When you pass the other way, right here, so you're passing through equilibrium, but on the way back, you're maximum positive velocity. Okay? And so there you go. You have the position as a function of time, and you have the velocity as a function of time. They're both sinusoidal, but the position as a function of time turns out to be the cosine, whereas your velocity as a function of time turns out to be the sine. Sine and cosine have the same shape. They've just been shifted over. And in fact, you can see that, if you take this like bump here, okay, and you shift it over, it would just match up with that one. All right. So there you go. There's the story of the position as a function of time and the velocity as a function of time and the relationship between the two. Let me zoom in again. Okay. And finally, how do we get the acceleration as a function of time from the velocity as a function of time? It's a slope again, okay? So let's take a look here. When you're at t equals 0, what's your slope? Well, the slope here would be negative, okay? So when your velocity is 0 at the endpoints, right, so there's the 0 velocity, you have a maximum acceleration in the negative direction. All right. When the velocity is maximum, that is when the oscillator is passing through equilibrium, the velocity is as big as it's going to get. Okay, but leading up to equilibrium, it was speeding up, and after equilibrium, it slows down. So if you're speeding up before and you're slowing down after, the rate of change must have gone through 0, and that's why right at equilibrium, where your velocity goes from speeding up to slowing down, your acceleration is 0. Okay, so there, when you have the maximum velocity, you actually have 0 acceleration. Again, when you're passing through the equilibrium on the way back, okay, or sorry, when you reach the endpoint, this is at a half the period. When you reach the x is equal to minus a, the velocity stops. The velocity stops, but the acceleration is maximum at those endpoints. Okay, and then when you pass through equilibrium on the way back, okay, you were speeding up before that, you're slowing down after that, so the acceleration is exactly 0 there. And then again, when you're back to the x is equal to plus a, and that is where you stop, where the velocity stops. Even though the velocity stops, you're being swung around as fast as possible. The rate of change, the velocity is 0, but the rate of change of the velocity is as big as it's going to get, and so you have a big acceleration, big negative acceleration, okay? And that's the relationship between the velocity as a function of time, velocity as a function of time, and the acceleration as a function of time. Okay, so the next slide is just kind of a little reminder of some values of sines and cosines. Sorry, that's too small. Sines and cosines that you really should memorize, okay? And the reason you should memorize them is not just for this particular lecture, which is on oscillators. The next lecture is going to be on vectors, and you will see that all through the course we're going to use sines and cosines, and we're going to be evaluating these at special angles, all right? And now those special angles, you know, you could always just do them on your calculator, but you know, it's good to have some intuition. Like, you don't have to know the value of sine and cosine at every single angle. I mean, I don't think any human being can do that. But if you know them at certain angles, you know whether you have some intuition as to whether your answer is right or wrong, and that's going to help you a lot to not make mistakes. In fact, on some of my tests, you almost don't need a calculator. Just by using your intuition as to how the sines and cosines work, you'll be able to work out the answer even without having to punch in, you know, cosine of some angle or whatever. Okay, and so so this is just a bit of an aside. All right, it's not directly part of the 1D kinematics, but since we've hit sines and cosines for the first time in the course, seriously hit them, we should probably look at that. Okay, so over here in this column, what I have is the cosine and radians. So cosine of 0 is 1. Okay, so you could do this on your calculator, put your calculator in radians mode, and do cosine of 0, and you'll get 1. Cosine of pi divided by 2, that's like a quarter of the period, okay? Because the full cycle is 2 pi, all right? So maybe I should start there. The full cycle is 2 pi. So if cosine of 0 is 1, then cosine of 2 pi is 1 as well. Why? Because you've made a full cycle. In other words, back to the graph here of the cosine, you start here, that's at 0. Where are you at 2 pi? You're there. Look, you're repeating the entire thing. So I didn't even draw past the cycle, because what would it look like past this? It would be the whole thing repeated again, but just shifted over. That's just how the cosine works, okay? And so over here, cosine of 0 is 1, so cosine of 2 pi is also 1, all right? Now, when you're at a quarter of the period, that's 2 pi divided by 4, which would be pi divided by 2, that's 0, okay? So at a quarter of the full cycle, cosine of pi divided by 2 is 0. Half of the cycle, cosine of pi is -1, and cosine of 3 pi by 2 is 0, and then again cosine of 2 pi is 1. Take a look here. The pattern is very simple, and remember, here we're going 0, and then a quarter of the cycle, half of the cycle, 3/4 of the cycle, the full cycle, and we go from 1, 0, -1, 0, and 1 again. Okay. If you think better in degrees, I have it here in degrees. So a full cycle, all the way around the circle, is 360 degrees. What's a quarter of that? Well, 90 degrees. So we have here 0, and then we have 90 degrees, and then another 90 degrees would bring you to 180, and then another 90 degrees would bring you to 270, and then another 90 degrees brings you to 360. Okay, so you can see here that you're going a quarter of the cycle all the way along here. All right, and cosine of 0 degrees, so if you put your calculator now in degrees mode and you do cosine of 0, you'll get 1. Cosine of 90 degrees is 0. Cosine of 180 degrees is -1. Cosine of 270 is 0, and cosine of 360 is the same as cosine of 0, and you're back to 1 again. Okay. Now you'll notice I've got this little bit here. Remember, when you hit 2 pi, you've reached the full cycle. So if you go back to formula number 1, when omega times little t, when little t is equal to capital T, that entire argument would look like omega times capital T is equal to 2 pi. That's the formula that I gave you. That's like equation number 2, where I have like omega is equal to 2 pi divided by t, okay? And so you can see that all of this is consistent. So I just bring this up to show you that, you know, once you've reached 2 pi, that you've made a complete period, that's one complete cycle. So if omega times capital T, because little t now is equal to capital T at one complete cycle, that must equal 2 pi, and that there is exactly the formula that I gave you above, which related the angular linear frequency and the period together. Okay, Um, well, we've done the sine, the cosine. Let's do the sine next. Okay, so we're still in this aside here. And now if you do sine of 0, and sine of 0 is 0. Okay, a quarter of the cycle later, sine of pi by 2 is 1. Sine of pi is 0. Sine of 3 pi by 2 is -1. And then when you're back to sine of 2 pi, you're back to sine of 0, which is 0. Okay, so notice the pattern here, 0, and then a quarter of the cycle later, plus another quarter of the cycle, plus another quarter of the cycle, plus another quarter of the cycle. You go from 0 to 1 to 0 to -1 to 0. Okay, so these are good numbers to memorize. I didn't put the degrees here, but they're obvious. This would be 0 degrees, this one would be 90 degrees, this would be 180 degrees, there's 270, and there's 360. Okay, so an aside, worth memorizing because you're going to see this come up over and over and over again. Okay. All right, and this next slide that I have here actually is an attempt to really nail all the pieces that I've set together. If you're still a little bit confused about what points in the cycle we're talking about, I redrew diagram number 1, okay? But now I've actually labeled the times on it, all right? So it's oscillating back and forth here like this, okay? So it's oscillating back and forth here like that. And at this point here, this is actually little t equals 0, okay? And by the time you get to here, this is a quarter of the cycle, so this little t is equal to 1/4 of the period. By the time you get to here, that's little t is equal to 1/2 of the period. And over here, you're at 1/4 of the period, and over here, you're back at t is equal to capital T. Okay? So at this point, if we say we're at x is equal to a, we're at that point, am I there at time t equals 0, or am I there at time t equals the period? The answer is yes. You're there twice. Both at the beginning of the motion and then at the end of the motion. Okay. Now, if we take a look at let me scroll down a little bit too far. Let me shrink that a bit. Let me see if I can get that in there. Okay. Yeah, that should work. You should be able to see that. Okay, so it's a little bit small, but I'll expand it again in a minute. Let's ask the question: at what point do you obtain your maximum values of either x, v, or a? Okay, so if we're at the endpoints here, and that is that x is equal to a, or is that x is equal to minus a? So just never mind the middle, never mind the equilibrium. Let's just ask at the endpoints. Let's ask ourselves, what is the value of x? Well, at the endpoints, by definition, your x is its maximum value. So at the endpoints here, all right, x is its maximum value. V at the endpoints is 0. So v is 0 there, and it's also 0 at this other endpoint over here. And also at the endpoints, your acceleration is maximum, and that's equal to omega squared times a. Okay, I proved that for the calc students. For the non-calc students, I'm just asserting that is true. Okay, without proof. Okay, so at the endpoints here, the value of x is its maximum value a, which is the definition of the amplitude anyhow. The velocity is 0, and the acceleration is also maximum. Okay, and you might wonder, why did I drop the negative sign there? Because I'm only worried about the maximum amplitude. Okay, so it's just, without like absolute values. I'm not worried about the direction. Okay, yeah, the direction of the acceleration at this point is in the negative direction, but just in terms of the magnitude, how big it is, it's just omega squared times a. Okay, now so there's the story at the endpoints. What happens at equilibrium? Okay, so let me expand this up again here. Okay, so there. Again, at the endpoints, x is at maximum value of a, velocity is 0, and the acceleration is at a maximum value of omega squared times a. Well, at equilibrium, this is at a half of the period, 3/4 of the period, and so on. Okay, I'm sorry, this should be 1/4 of the period. I apologize. Okay, I realize that's a mistake. So that's a quarter of the period, 3/4 of the period. Let's look at the diagram again so that we're not going to make any mistakes. So we're at a quarter of the period or 3/4 of the period. There, like that. Okay. When we're at equilibrium, well, at equilibrium by definition, x is equal to 0. Okay. That's when you're going to get your maximum velocity, but the acceleration is 0 at the end. Okay. And so we have this interesting situation where if we compare the endpoints to the equilibrium, at the endpoints you have maximum x and you have maximum a and 0 velocity. And at the equilibriums, you have x is equal to 0, the acceleration is equal to 0, and you have maximum velocity. So where x and a are maximum, the velocity is 0. And where the velocity is 0, okay, sorry, where the x and a are 0, that's where your velocity is maximum. All right. And so I have here yet another way of thinking about this. All right. Where does maximum x occur? Well, maximum x is by definition your amplitude. That occurs at the endpoints. Where does your maximum velocity occur? Well, that occurs at equilibrium, and that's going to be a maximum velocity of omega times a. All right. And where does your maximum acceleration occur? Your maximum acceleration occurs at the endpoints, and that's going to equal omega squared times a. All right. Conversely, x is equal to 0 at equilibrium. That's the definition of equilibrium. Okay. Your velocity is equal to 0 at the endpoints, and your acceleration is equal to 0 at equilibrium. Okay. Now, why is it important to know this? Well, because when we go to solve word problems, I'm going to be really concentrating mostly on these formulas right here. Okay. So these are the formulas that we're going to be using, along with equation number 2 above, which relates omega to f and t. And these equations here, that's the equations we're going to use to solve our word problems. Okay, we're not going to use the sines and cosines right now. Okay, and so in a word problem, I may not say endpoint or equilibrium. I might say where the velocity is maximum. Okay, and I expect you to know that the velocity is maximum at equilibrium. So I'm going to expect you to know that the maximas of position, velocity, and acceleration occur either at the endpoints of the equilibrium, respectively. Okay, and I'm going to expect you to know that the velocity is 0 at the endpoints and that the acceleration is 0 at equilibrium. All right. So having said that, let's just jump into one of our problems here. Okay, and so here we have an example. An oscillator has a maximum velocity of 5 meters per second and a maximum displacement of 10 centimeters. Okay, so there's the situation. I just set that up for you. And take a look at how I worded this. Okay, so I say an oscillator has a maximum velocity of 5 meters per second. I said maximum velocity, but I expect you to know that maximum velocity occurs where? It occurs at equilibrium. Okay, so here you'll notice that I put this kind of like a little bracket up here, and what I'm saying is, like, when you see a word problem like this in a test or one of the little quizzes, you'll see maximum velocity, but I expect you in the back of your mind to understand that maximum velocity occurs at equilibrium. Okay, and we'll see that as the word problem goes on. All right, so. Okay, great. We've set up the situation. We have an oscillator. It has a maximum velocity of 5 meters per second and a maximum displacement of 10 centimeters. Okay, and question number 8 is, what is the amplitude? Well, that's actually trivial. I'm just expect you to know that what you mean by amplitude is maximum displacement. So if I say maximum displacement or I say amplitude, I'm really saying the same thing. So the amplitude is the maximum displacement. That's just 10 centimeters. And better convert this to MKS, because you can see here the 5 meters per second is MKS, but the centimeters is not. And so the amplitude, 10 centimeters, that's the same as 0.10 meters. Okay? So there we go. That answers question A. Question B is, what is the angular frequency? Okay? Now, what do we know? We know that the amplitude is 0.1 meters. We know that the maximum velocity is 5 meters per second. And you ask yourself, is there an equation that relates the two? Okay. Now, I gave you lots of equations above, so maybe this is the point where I should really emphasize what equations you need to know. You need to know these equations here. A, that maximum x is equal to a, maximum velocity is omega a, and maximum acceleration is omega squared a. You need to know those. And you need to know this other one. Let me scroll all the way back here. You need to know this one right here, okay? This equation there, which relates the angular frequency to the linear frequency to the period, okay? So equation number 2, along with these other equations here, are what you would actually need to solve problems, okay? All that other theory, don't throw it away. We'll need it later in the course, but for the problems that we're doing right now, what I just showed you is what you need, okay? And so back to our problem here, part B was, what is the what is the angular frequency, we know that A is equal to 0. We know that Vmax is 5 meters per second. And you look at those equations above and you go, well, which one relates amplitude and maximum velocity and angular frequency, because that's what we're trying to find. And it's Vmax is equal to omega times A. Okay? So Vmax equals omega A. You know Vmax, 5 meters per second. You know A, 0.1 meters. That allows you to solve for omega. So I just rearrange the formula. I divide both sides by A, and I get omega is equal to Vmax divided by A, like that. And so now I can I can substitute in the numbers. Vmax, I told you, was 5 meters per second. A, we found in the previous question, is 0.1 meters. 5 divided by 0.1 is 50. All right, and now let's take a look at the units. So here we have meters per second, and in the numerator. In the denominator, we have meters. So the meters in the numerator and the meters in the denominator, they cancel. So what's left? Just the per second, the 1 over second. So it's 50, so omega is equal to 50 per second. Now this is written as 1 over second, but it's kind of awkward to say 51 over second. So usually we say 50 per second. 50 what per second? 50 cycles per second. But it's omega, so there's actually that 2 pi in there. But yeah, it's still 50 per second. And I'm going to introduce a new unit. It's really not a new unit, but it looks like a unit on its own. It's really per second. It's really seconds. It's called hertz. And whenever you have 1 over seconds, we could just write that as hertz, okay? And that's a measure of frequency. You've probably heard of hertz before because I don't know if anyone listens to AM or FM radio anymore in their car, but there's AM and FM radio, and if you look at the frequency dials on the AM and FM radio, the AM is in kilohertz, and the FM is in megahertz, okay? Kilo just means 1,000, mega just means million, okay? The hertz, what is that? Per second. So what are those hertz there? It's the number of cycles per second in the frequency of the radio waves. Okay, and so you're going to see hertz very often. There's nothing wrong with writing the units as 1 over second like that. That is correct. And, seconds are the MKS units. But it's just become tradition to write 1 over second as hertz, okay? And so in the course, you'll see both of these, all right? Especially when it comes to, frequencies, when we're talking about radio waves in the second half of in the second semester, you'll see hertz quite a bit, okay? So there it is. So hertz is the MKS unit for frequency just because it's 1 over second. Okay, all right, great. So omega is equal to 50 hertz. All right, that answers the question. Question C is, what is the maximum acceleration? And again, if you take a look above, you'll see that an equation that relates A max, the maximum acceleration, the amplitude, and the angular frequency is A max is equal to omega squared times A. Okay, and we know omega and we know A. We just solve for those things, and so we can plug in. Omega is 50 per second, and A is 0.1 meters, okay? And so if you do 50 squared times 0.1, you get 250, and that's how the number comes about. Let's take a look at the units, because you'll see that the units actually work out, okay? So A has units of meters, so there you go. There's the meters in the numerator. And what about the denominator? We have 1 second, but then it's squared. So it's not just per second, but it's per second squared. And the units work out because you know that the units of acceleration are meters per second squared. Okay, so usually I don't plug in the units into the formula, but just in this particular case, I wanted to show you, or even in the previous problems, I wanted to show you that the units actually do work out to what we expected. In a previous lecture, I showed you that the units for acceleration are meters per second squared. And, does meters per second squared come out of this formula? Yes, it does, because you get a per second squared here, and you get a meter here, so you get a meter per second squared. So the answer, that the maximum acceleration is 250 meters per second squared. Okay. What is the period of the motion? Well, the period of the motion, you have that omega is 2 pi over capital T. That was that equation 2 above. Okay, and just rearrange that, multiply both sides by capital T, divide both sides by omega. You get that T is equal to 2 pi over omega. Well, we have omega. Well, pi is just 3.1415. I've got too many significant figures there, but that's okay. We'll just round off the 3 significant figures in a second. So 2 times 3.1415 divided by 50 gives you 0.126. So the period is 0.126 seconds. Do the units work out? Well, the omega brings in a per second, but that's in the denominator, okay? And when you have 1 over 1 over second, the reciprocal of a fraction is you just flip them. And so the seconds, which is in the denominator of the denominator, comes up into the numerator. Okay, it's a little bit complicated, but I think you got it. Okay, so because this is 1 over seconds, when you put that into the denominator, it comes up on top into seconds. And so the units work out there too. Okay, and so the answer is, the period is 0.126 seconds. That's actually pretty fast. You know, that's like a little more than a tenth of a second. It'd be, you know, hard to see this thing wobbling back and forth, because it would just take a tenth of a second for 1, and it would wobble back and forth roughly 10, more like 8, because I'm rounding off a bit, but like it would oscillate back and forth like about 8 times in a second, which is pretty fast. Okay, so there it is. There's the lecture. As usual in my lectures, you know, there's a lot of theory that doesn't apply directly to the immediate problems. Okay, and don't throw that theory away. Don't just say, oh, I can forget this because I won't actually need it for these problems. No, the whole course holds together. So this theory comes up again later. Okay, not immediately, but it will. Okay, you'll see it again in uniform circular motion. You'll see it again in dynamics. So don't just, you know, brain dump that and go, oh, I'm just going to memorize how to solve the problems because that's all I'm expected to do on the test. Yeah, that's true for this section, but when it comes to the future sections, you know, I'm going to be pulling some of the stuff out of the theory that I've given you, and so you will need it. Okay, I'm giving it to you here because this is the appropriate place to give it to you. Okay, and just to summarize the kinds of questions that you would get here, this is a very typical question. Okay, so you'll see more in the quizzes and in the little tutorial videos that I'll do together as a live stream. Okay, everyone, there it is for this lecture. Thank you.